The universe is vast and ancient. It is filled with billions of galaxies, each containing billions of stars. But even the universe has an end. Scientists have long pondered what will happen to the cosmos we inhabit. What will be the ultimate fate of stars, galaxies, and even space and time itself? Our current understanding suggests that the universe is expanding. This expansion is thought to be driven by a mysterious force called dark energy. As the universe expands, it cools and becomes less dense. Eventually, stars will burn out and galaxies will drift apart. What happens after that is a matter of speculation, but physicists have developed several theories about the universe's ultimate fate. These theories are based on our current understanding of physics and the observed behavior of the universe. To understand the end of the universe, we must first understand its beginning. The prevailing cosmological model is the Big Bang theory. This theory suggests that the universe began from an extremely hot, dense state about 13.8 billion years ago. Since the Big Bang, the universe has been expanding and cooling. Evidence for this expansion comes from the redshift of light from distant galaxies. This redshift indicates that galaxies are moving away from us. The farther away a galaxy is, the faster it appears to be moving. The expansion of the universe is a key factor in determining its ultimate fate. If the expansion continues indefinitely, it will lead to a cold and dark future. This scenario is known as the heat death of the universe. Heat death is the most widely accepted theory for the end of the universe. It is a concept that has intrigued scientists and philosophers alike for many years. It is a bleak scenario in which the universe continues to expand and cool until it reaches a state of thermodynamic equilibrium. This means that the universe will keep getting larger and colder, with galaxies moving farther apart. In this state, all matter and energy will be evenly distributed throughout the universe. There will be no regions of high or low energy, just a uniform spread. There will be no more stars, no more galaxies, and no more life. The processes that drive the formation of stars and planets will cease. The universe will become a cold, dark, and empty place. It will be a vast expanse of nothingness, devoid of any form of life or activity. Heat death is a consequence of the second law of thermodynamics. This law is a fundamental principle of physics that governs the behavior of energy in the universe. This law states that the entropy of a closed system always increases over time. Entropy is a measure of disorder or randomness, and it tends to increase in any natural process. Entropy is a measure of disorder or randomness. In the context of the universe, increasing entropy means that energy is becoming less and less concentrated, spreading out more evenly. In the context of the universe, increasing entropy means that energy is becoming less and less concentrated. As the universe expands, this process accelerates, leading to a more uniform distribution of energy. As the universe expands and cools, energy will become more evenly distributed. The once vibrant and dynamic cosmos will gradually fade into a state of uniformity. Eventually, there will be no more energy gradients to drive any kind of activity. The forces that once shaped galaxies and stars will no longer be at play. The universe will reach a state of maximum entropy, where nothing can happen. It will be a silent, motionless expanse, marking the ultimate fate of all that exists. While heat death is a gradual and relatively peaceful end to the universe, other theories propose a more violent demise. One such theory is the Big Rip. This scenario suggests that the expansion of the universe will accelerate at an ever-increasing rate. This acceleration is thought to be driven by dark energy, a mysterious force that makes up about 68% of the universe's total energy content. If dark energy's strength increases over time, it could eventually overcome the gravitational forces holding galaxies, stars, and even atoms together. In the Big Rip scenario, the universe would be torn apart. Galaxies would be ripped apart first, followed by stars, planets, and even atoms. This would happen in a finite amount of time, perhaps tens of billions of years from now. The Big Rip is a relatively speculative theory. However, it is a possibility that cannot be ruled out based on our current understanding of physics. Section 5. The Big Crunch. A return to the beginning. In contrast to the Big Rip, which posits an infinite expansion, the Big Crunch proposes a reversal of this expansion. Instead of galaxies drifting apart forever, they would start to come back together. This theory suggests that the expansion of the universe will eventually slow down and reverse. Imagine a cosmic brake being applied, causing everything to decelerate. The universe would then begin to contract with galaxies moving closer together. This contraction would be a gradual process taking billions of years. As the universe contracts, it will become hotter and denser. The energy from this contraction would cause temperatures to rise dramatically. Eventually it will collapse in on itself, returning to the extremely hot and dense state from which it began. This final collapse would be a cataclysmic event. The Big Crunch is an intriguing theory because it suggests that the universe might be cyclical. Just as the tides ebb and flow, the universe could expand and contract in a never-ending cycle. After the Big Crunch, a new Big Bang could occur, creating a new universe. This new universe would be born from the ashes of the old one, starting the cycle anew. This cycle of expansion and contraction could repeat indefinitely. Each cycle would bring about a new beginning, a fresh start for the cosmos. However, like the Big Rip, the Big Crunch is a speculative theory. It is one of many ideas that scientists have proposed to explain the ultimate fate of the universe. Current observations suggest that the expansion of the universe is not slowing down. In fact, it seems to be speeding up, driven by a mysterious force known as dark energy. In fact, it appears to be accelerating. This acceleration makes the Big Crunch scenario less likely, as the universe seems destined to expand forever. This makes the Big Crunch scenario unlikely. Yet the idea remains a fascinating possibility, reminding us of the many mysteries that still surround our understanding of the cosmos. Section 6. The Degenerate Era, Stellar Remnants. Regardless of whether the universe ends in heat death, a Big Rip, or a Big Crunch, the stars we see today will not last forever. Stars are powered by nuclear fusion, which converts hydrogen into helium in their cores. Eventually, stars will run out of hydrogen fuel. When this happens, they will leave behind stellar remnants, such as white dwarfs, neutron stars, and black holes. White dwarfs are the remnants of low-mass stars like our Sun. They are incredibly dense, with a mass similar to the Sun's but a volume comparable to Earth's. Neutron stars are the remnants of more massive stars. They are even denser than white dwarfs, with a radius of only a few miles. Black holes are the remnants of the most massive stars. They are so dense that nothing, not even light, can escape their gravity. Section 7. Black hole evaporation and the end of time. The degenerate era, dominated by stellar remnants, will last for an extraordinarily long time. This era will be characterized by the slow decay of the universe's most resilient objects. However, even these objects will not last forever. Over unimaginable timescales, the universe will continue to evolve, and the remnants of stars will undergo further transformations. White dwarfs and neutron stars will slowly cool and fade away, becoming cold and inert. These once bright beacons of the cosmos will turn into dark, lifeless husks. Black holes, on the other hand, will eventually evaporate through a process called Hawking radiation. This phenomenon is a fascinating aspect of theoretical physics. Hawking radiation is a theoretical prediction by physicist Stephen Hawking. His groundbreaking work has provided deep insights into the nature of black holes and quantum mechanics. It suggests that black holes are not entirely black but emit a faint thermal radiation due to quantum effects near their event horizon. This radiation is incredibly weak but persistent. This radiation carries away energy from the black hole, causing it to slowly lose mass and shrink over time. The process is slow but relentless, leading to the eventual demise of the black hole. This process will take an incomprehensibly long time, but eventually even the most massive black holes will evaporate completely. The universe will witness the gradual disappearance of these cosmic giants. The evaporation of the last black hole will mark the end of the degenerate era and the beginning of a truly empty universe. A universe where the fabric of space-time itself will be devoid of any significant events. Time, as we understand it, may cease to have meaning in a universe devoid of any events or changes. In this desolate expanse, the concept of time could become irrelevant, marking a profound shift in the nature of existence. Section 8. Philosophical Implications. Our place in the cosmos. Contemplating the end of the universe can be a humbling experience. It reminds us of the vastness of the cosmos and the transient nature of our own existence. Our planet, our star, and even our species are but fleeting moments in the grand scheme of things. The ultimate fate of the universe also raises profound philosophical questions. What is the meaning of life in a universe that is destined to end? Does our existence have any significance in the face of cosmic oblivion? These questions do not have easy answers. However, contemplating the end of the universe can help us appreciate the preciousness of life and the beauty of the cosmos. It can also inspire us to make the most of our time in this universe, however brief it may be. Section 9. Conclusion. The universe's unfathomable fate. The end of the universe is a topic that has fascinated and perplexed scientists and philosophers for centuries. While we have developed several theories about how the universe might end, the ultimate fate of the cosmos remains one of the greatest mysteries in science. Whether the universe ends in a whimper or a bang, in fire or ice, the end is likely billions, if not trillions of years away. In the meantime, we can marvel at the vastness and complexity of the universe we inhabit. We can continue to explore the cosmos and unravel its secrets, inching closer to understanding our place in the grand scheme of existence.